Hi everyone. Hope you've all been having a really good EuroRust. I know I have. A dog licked my ear half an hour ago, so that was already a great moment, regardless of any technical content. My name's Adam. I really love building APIs, but also I really hate maintaining APIs. There's no worse feeling than finally shipping this beautiful, perfect, handwritten API into production, and it works great, and then someone requests a feature, and then you've got to go and update it. And then what do you do about all the old clients that don't know about the new feature? It's painful. And I'm a recent convert to the art of code generation. And like any recent convert, I'm a real evangelist about it. So I'm going to walk you through how to remove toil and repetitive labor from your life. Like I said, I'm Adam. I used to work at Cloudflare, where I did a lot of APIs in Rust. Then I saw a tweet from the CEO of a startup looking to hire someone to build APIs in Rust, and I thought, okay, look, maybe there's something there. I blog at adamchalmers.com, and that's me on the right there. We're going to talk about APIs today, and we're going to specifically talk about keeping APIs correct. So we're going to talk about APIs, servers, and clients, and schemas, this beautiful little three-way handshake. Then we're going to talk about some problems with these systems, and then we're going to talk about the solutions. The solutions are out there that you can use, but also solutions you can make for yourself, because the world of software is always changing. There's always cool new languages coming out, and so the tools you have today will not be the tools you want to have tomorrow, and you can wait for someone else to do them, or you can make your own. And if there's one thing I want you to leave this talk with, I want you to feel empowered to make your own tools and write your own code to do whatever you want to be able to do. So I hope you feel empowered after this. Why do I care about APIs at the moment? Why does my employer give me the time to work on these APIs? I work at a place called Zoo. We're making CAD software, computer-aided design software. Here's a screenshot of an app we make. It's got a really exciting name. It's the modeling app. We're working on a new name. If you have any suggestions, please let me know. This is a kind of code for CAD app. You can see you write code on the left, and you get these visuals on the right, kind of like Markdown, but for 3D geometry. The big thing is that all of the visuals there are not rendered on your device. They're rendered in the cloud, so you can use latest and greatest giant big GPUs from NVIDIA or whoever without having to buy one or try to run it in your laptop and have it eat through your laptop battery in 20 seconds or so. So all the video rendering happens off device. Everything we do at Zoo is API-driven. You don't have to deploy it on your own local devices. You can use it through an API. And this way, if you don't like the UI we've built here, if you think my programming language is shit, then find me afterwards and tell me, and we'll fight about it. But if you actually don't want to use this app, you don't have to, because we make an API. And so you can build whatever CAD software you want on top of our API. At RustConf a few months ago, I met a guy who worked at a sheet metal foundry. And he had all these back and forth calls with customers because their foundry can only manufacture so many different kinds of metal at different curvatures and everything. And so he'd have to get the CAD file from his customer, and he'd look at it, and he'd open it up, and he'd say, we can't manufacture this. I've got to call the customer back and tell them what to do. And they go through this whole cycle back and forth of tweaking the files. So instead, he said, right, we're just going to make our own CAD app. And it's a CAD app that perfectly captured the constraints of what his foundry could produce. So you get real-time feedback as you're designing, right? We all love Rust. We all love getting feedback at compile time. Designing in CAD is kind of like compile time for real-world objects. So you want to get the notice that you can't actually manufacture it as early as possible to save you time. So making your own CAD app is a lot of work. And he was saying, God, I wish there was something like Zoo at the time, because I wouldn't have had to build the entire geometry engine and 3D renderer for myself. So we have an API that lets you focus on your business logic, your manufacturing constraints, your customers, and you can hand off the geometry parts and the 3D rendering to us. So having an API-driven business means we really care about making this API easy to use. If our API sucks, no one's going to use it. We don't make any money. If our API is inaccurate, no one knows how to use it. We don't make any money. So we really care about API correctness, and probably a lot of you do as well. So here's roughly a map of how APIs tend to work. You've got some kind of server that has some operations available on it. You have clients that can send requests to the server, and they can say, hey, server, go do this. The server does that, tells it. How do the client and server know what each other are doing? How do they know what operations are available? How do they know what data to send and what data to receive? There's a schema. A schema is like a voluntary contract. The client and the server shake hands and agree that this is going to be how we communicate with each other. So this is all great. You have a client talks to server talks back. They both conform to a schema. Great, problem solved. What is a schema, actually? It's very vague. Schemas need to be human readable, right? A schema can just be a text file that you send to your UI team that describes all the endpoints you have available and what to send. And that works totally fine. I've shipped schemas like that. If you know you're only building for one kind of person, you can just say, hey, here's the schema. We support get at this URL, and we return back bytes. That's fine, but for a lot of use cases, that's not going to be enough. So you may want your schema to be machine readable as well, right? If it's machine readable, then your client and server can check, am I keeping up to date with the schema? And they'll warn you if you're trying to do something that's impossible for the schema. So ideally, you'd like to have the schema be both human readable and machine readable. Right? There's a lot of standards out there for this. We're going to mostly talk about OpenAPI, which is a standard that used to be called a whole heap of different things, and it's evolved a whole heap, but it's quite a popular standard now. And it's an open ecosystem. We're going to come back to this point. There's a lot of other alternatives out there. You maybe want to use gRPC or Captain Proto or so many other standards. Seriously, there's so many other standards out there. So we're going to go through an example of what an OpenAPI schema looks like. We're going to have just a pet shop is the canonical example. We're going to look at one endpoint that lets you get a pet by its ID. And I apologize, because I'm going to do something really awful right now, something that I don't think anyone else has been brave enough to do here and expect the audience to like them. I'm going to show you a big old JSON file. And I'm really sorry in advance. No one likes reading JSON, but we're going to do it anyway. So here's a little example. Here's a pet. This is the palette cleanser to get you ready for a big JSON file. That's my dog, Leo. So here's an example OpenAPI schema. A schema is basically a list of what properties a type has. So the OpenAPI spec defines a bunch of operations. You can see we've got some operations like under the paths, we have a list of paths and HTTP verbs. So an operation is just a combination of path and verb. You send a get to pet/pet ID. Operations have some human-readable fields, like the summary, and they have some fields that are meant for machines as well. But they also describe all the parameters that go into the request. And you can see here the parameter describes the pet ID that you see in this path over here. That's a parameter that can be an integer. So when you go into a URL, it'll be /pet/33 or something. And it shows you in a kind of human-readable and machine-readable way exactly what the constraints that data has to meet are. And you can see the responses the endpoint gives you. It shows you if you get an HTTP 200, everything OK, then this is what you'll be sent back. You see here another schema. This schema is not defined. It's actually defined somewhere else. So you get a reference to somewhere else in the schema. This way, shared types that you use all over your API, like a pet, you can define once in one place, and you can reference them from the JSON file. This is minimizing the amount of JSON you need to read, which is really kind, because you should need to read as little JSON as possible. Again, I apologize for this slide. What is a schema actually? What does it look like? Here's that pet schema from before. It referenced this field inside the OpenAPI spec. You've got this part components, you've got this part schemas, and you have a list of them. So the pet is a type. It tells you what type is it. It's an object. And for every property that object has, it tells you the property's name and its possible values, its type. So you can see this is nullable. It's going to be an integer. It tells you what the name is and everything. You have another field called photo URLs, which is an array of strings. And it's got, oh, interesting, it's got to be exactly 2 items. So you can do some constraints you wouldn't always be able to do. Not all languages have a way to support the number of elements in an array. But OpenAPI, it's a little more sophisticated. It's not great, but it's good enough, generally. So yeah, that's a lot of JSON. I apologize again. This is technically human-readable. And the word human-readable is a really low bar. Moby Dick is human-readable, but no one actually enjoys reading it. And I feel the same way about JSON. So luckily, there's a whole heap of tools around there to make OpenAPI more pleasant to consume. This is some example OpenAPI documentation generator. So if you don't like reading JSON files, you can instead look at this. I think this is much nicer to look at. And this works because it can take in the OpenAPI spec.json, and it can output this nice, beautiful HTML page. And this works because OpenAPI is a standard ecosystem. There's a definition of the spec. And you can write tools that consume an OpenAPI file and give you something better, like this. This is from some company called bump.sh. Maybe it's pronounced bumpsh. I'm not sure. But I just kind of found it looking around. It was the prettiest one. This is not an endorsement. I don't know how it works. So we have this schema. We can understand it. The machines can understand it. It's all great. Sounds great. There's only one problem, which is that schemas can change, right? Servers will change. And then when you add a new field to your server, the schema needs to change. And someone has to do that. So at least in my experience, every human I've ever worked with has been fallible. And so you forget to do little operational tasks like this. You'll forget to update the schema, and then you'll get a message from an angry user, or a test will start failing somewhere, or the other people you work for who supply the client team won't know about the change. So at Cloudflare, we kind of solved this by having this service that would periodically probe production, and it would make sure that the schemas that you have published are actually correct in production, that the production actually matches the schema. This isn't a great solution because tests are tests are good. Don't stop writing tests by any means. But tests are only ever going to be able to test a partial subset of the functionality you have. I prefer to kind of design it in such a way that the test is kind of inherent in the system. And this is hard, but I think it's worth it. So a better idea is don't handwrite the spec. Don't rely on a programmer updating the spec. Instead, have your API server generate the spec. Because whenever your server changes, it can generate a new copy of the spec, and you know it's correct. Whenever the server changes, it generates a spec, and it's kept in sync. So how do you do this? You can basically automate the API toil. So there's a lot of great Rust web servers out there. One of the great things about Rust is its macro system. One of the terrible things about Rust is also its macro system. But it's very powerful and very much worth it, in my opinion. I think macros are kind of like salt. You want to use a little, it's basically unusable without a little bit of salt, but you really don't want to pour too much in or you'll also ruin the entire meal. So careful use of macros is kind of essential, I think. This is an example web service that does the pet shop that we showed before. This is from a web framework called Dropshot. It was built at Oxide Computer by the smart folks there. And our startup has some shared founder DNA with Oxide. So when our founder went to start this one, she brought Dropshot with her. So you can see here you have a web server. It's got an endpoint. It's got some parameters it takes in. And it has this endpoint macro on it. This lets the Rust macro look over the type signature of your endpoint. And it knows, OK, this consumes a path parameter. And I can look up the type of this path parameter struct, and I see everything it contains here. And it implements this trait JSON schema from the schema-rs crate, or schemas, as it might be pronounced. And so it can generate the right JSON schema for all the types we need in our server. And so overall, Dropshot can just generate this spec.json from it. It's really nice. It really beats having to handwrite a spec yourself. There's a lot of support in other frameworks. I know we have Rob from Actix Web somewhere in the conference, and I believe there's a whole ecosystem of things out there for your favorite web services and your favorite web frameworks to automatically generate OpenAPI support. It's still a bit of a niche use, but it's really rapidly growing. So once you can automatically generate the schema, how do you keep it in sync? The way we have chosen to do it at KittyCAD is we basically use CI. So on every PR, we have a test in the code base that runs the Dropshot schema generation, and it compares the schema that we have stored on disk in the repo root. And if they're different, it fails CI, and you get a message telling you, hey, regenerate the OpenAPI spec.json, and you've changed something, and the spec.json in the repo root is stale. So now we know that whenever a PR is merged, if it changed the server, it changed the spec too. And then we can find everything that consumes the spec, or maybe not everything, that's a bit ambitious, but a lot of the services that consume the spec. And whenever we merge to main, we have another GitHub action that triggers, and it opens up a PR to the repo, and opens up a PR that updates that spec.json. So you can see some YAML. Again, I'm sorry, I've been putting JSON and YAML on all these slides, very unpleasant, but whatever. You can see we're using some YAML here to just basically open a new commit to another repo, commit the changed spec, and then open it up as a PR. You can see the resulting PR down below in the corner of the slide. So what is actually consuming these specs? The API clients consume them. There's two main kinds of API clients. There's these general-purpose clients that just do web requests. So curl in the terminal. Postman is a GUI that does it. You can even have general-purpose clients in programming languages. So JavaScript has this neat little fetch function that'll basically do any HTTP request you want. So these clients can interface with any API, including mine. On the other hand, there's also purpose-built web clients that really just hit one service in particular. Sometimes these are called software development kits or SDKs. These are basically packages that let you use an API from your favorite programming language. So we obviously we love Rust so much at the company. Basically everything in the company except the very, 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 very front of the front end is JS. The very, very back of the back end is C++ and CUDA. And everything in between, the remaining 80%, is Rust. So we have a Rust API It's a Rust SDK. You can just import. You can use kittycat in your code. You can add the kittycat.toml, add kittycat to your cargo.toml, and you can just start using Rust within your code. This is, I think, a vastly superior experience because shelling out to use curl or something is always going to be a bit tricky. You want to really, if you're serious about making your APIs usable, you really want to have your own crate or package or wheel or whatever weird little term of art any language uses. So again, you've got these clients, and you've successfully been updating the schema. Great. But how do the clients actually get the new schema? You're going to need another PR to update the schema, and if you're doing this by hand, again, you will forget, and people will get mad. You'll get an angry email from your users. Fun little fact, before I started working for Jess Frizzell, the CEO of Zoo, I worked at Cloudflare, where I maintained the official Cloudflare Rust API client. I didn't intend to, but we were a fairly early adopter team at Cloudflare, and we needed to make some API calls. We thought, oh, let's not just make an API call. That would be too straightforward. Let's make a fully general purpose Cloudflare Rust API client that can handle making any API call, right? Premature abstraction. That's really, really good, right? So we found ourselves maintaining the Rust API client for Cloudflare, and we weren't paid to do that. We were paid to ship features. So we were always a little bit behind, or very, very, very behind on the latest schema changes. And eventually, I got an email from my manager's manager, forwarded all the way down to me, angry email from Jess, basically saying, hey, there's a bunch of PRs building up, and the API schema you've published that says it's official isn't actually accurate, so would you mind merging all these PRs that fix all the problems with your API client? And so, sorry about that, Jess, if you're watching this. I don't think I've actually told her that yet, so this is how everyone in the audience finds out. So you really want to make sure that if you want to make a good impression on your future boss, you want known as the person who's got a really stale API client. How do you do that? Well, you don't manually keep your API clients up to date. You use code generation, right? If you can stop writing your API clients by hand, you can instead generate them automatically whenever the spec changes, just like we automatically generated the spec whenever the server changes, then you don't have this problem anymore. So we'll just write a fully purpose general API generator for API clients, right? That should be straightforward. It takes a bunch of work. The good news is there's already a bunch of solutions out there. So I hope it's clear why you might want to do this, because you don't want to do all the work of maintaining these API clients by hand. And especially if you want your API to be successful and you want to ship to a whole heap of different languages, you really don't want to have to maintain, be updating by hand a Rust client and a TypeScript client and a Go client and all these other languages, trust me. So we use a bunch of generators for this. There are a lot of solutions out there. There's language-specific ones, there's cross-language ones, there's paid ones, there's open-source ones, and these all basically take in an OpenAPI spec and will create a client in some language that matches that spec. Saves you a lot of work. I'd like to tell you how to make your own of these, because we weren't really happy with the state of them when we started the company, and we thought we could do better. Maybe a bit hubristic, but no point in not trying, right? I'd like to make sure that people get an idea for how these tools work, because OpenAPI is an interesting ecosystem. It's still a bit immature, and it's also always growing. So as we make new languages, someone's going to have to make the tooling for them. And when I started working at Zoo, I was very impressed and also intimidated by these code generators. I'd never really done it before, and I thought of them as a bit magical. And I thought, if I give a talk about it, that will force me to really understand them. Otherwise, I'll just embarrass myself on stage. So I want to make sure people can leave understanding how OpenAPI tooling works, because you will find a gap, or you'll find a tool that you don't like very much, but it's kind of the best thing out there, and you don't have to settle for the best out there. You can make your own too. So OpenAPI Tool is our Rust API client creator. It basically takes in an OpenAPI spec.json file as its input, and it analyzes it, figures out the structure, and it outputs a Rust crate. I want to be clear, it outputs a Rust crate on disk, so it'll output, a source directory and a cargo.toml file and a bunch of .rs files. It doesn't use macros. It doesn't create this inline. It's outputting normal Rust code. And this is, I think, a really good approach, because as much as I do like using macros, they're so hard to debug. And they can have some kind of transparent problems. It's really easy to output invalid code. Some people may have seen Sasha's talk yesterday about how easy it is to just output complete garbage from a Rust macro and get really confusing compile errors. Some people may have seen the talk from Lucas about Rust Analyzer trying to give you good error messages inside macros. They're powerful, but if you can write handwritten code instead, do that. And so we have a machine to output normal Rust code, not macros. And I think it's nice because you can then just open up the crate and look at it like a normal Rust crate. You can run cargo check. You can see everything. You can open PRs, and you can have diffs to it. So our tool outputs normal Rust code onto your disk like you would have gotten from running cargo new --lib. This has also been really useful because, like I said, we run our company in Rust. And this includes things like HR. We have a service called the CIO, the Chief Information Officer. It's not a person, it's a program. And so all of our employee management is done by having a big YAML file that defines all the employees, and the CIO takes it in, creates all the right groups, the Google groups and GitHub groups and Zoom permissions for them. And Rust is a great language, but a lot of these big SaaS companies don't publish Rust API clients. Your banking provider of choice probably doesn't have a Rust client, so you can establish payroll. So we found ones that had OpenAPI specs, then we generated our own for them. OpenAPI tool is open source. You can find it at the URL over there. Feel free to open PRs, but it's really it's built for our use cases, and we're probably not going to be wanting to make it more complex than our use needs. But feel free to fork it or just use it as a learning experience. So how does it actually work? OK, I got my slides out of order. I already talked about the beautiful advantages of normal Rust code. Basically, what it does is it constructs Rust source code using strings. Specifically, it uses the quote crate to kind of build up Rust syntax that we know is roughly correct, and then we render those as strings eventually. So you can see some example code on the right. We are basically slowly constructing Rust syntax inside our program. And then we write them out to disk, and then we can run cargo check to make sure we didn't produce any bogus, crazy output, we didn't have some invalid syntax. We also run cargo clippy on it with that flag that fixes it. Yeah, cargo clippy --fix. So we know that if there's anything straightforward that we could have done in our code generator, but it would have been a bit painful to, we can just run clippy fix on the output and make sure that it's roughly as good idiomatic Rust code as we can make it. So I'm going to walk you through what a crate from OpenAPI tool looks like and how it works. Basically, every operation, this path and verb pair, like get a pet from a certain URL, becomes a Rust function. It's going to be an async Rust function. And we generate examples as well. So you can see here the docs for the kitty cat crate. This is generated by OpenAPI tool. So it generates an async function that takes in the right kind of parameters. If it's got a body parameter, it'll take in a body parameter. If it takes in a query, it'll take in that in the parameters normally. And then if it's successful, it outputs the right type that the schema said it would. If it's an error, it defines an error type. This looks like a standard Rust crate. We even generate examples. I'm really proud of the example generation. I think that's you shouldn't be shipping a Rust crate without examples. And even if you're generating them, you can generate an example too. We basically look at a struct, and we look at every field, and we generate an arbitrary choice of value for that field. And if that field is of a type struct, then we kind of recurs down, and we generate the start and end of that struct, and then we generate all the fields within that struct. So it's quite nice to be able to have the ability to automatically generate examples because, again, this business fails if no one uses our API, and no one's going to use our API if it sucks. So making the API as easy to use as possible is a big deal for us. So we generate a function for each endpoint. These endpoints take in types, maybe in the body, maybe in the query parameters, maybe the return types. We have to generate the types too. Every OpenAPI schema becomes a Rust type. You can see here the example. We define a schema in our spec called angle. An angle has two fields. It's got a unit and a size, so it might be 360 in degrees or 2 pi in radians. And we generate a Rust struct from it. Not all types are structs. So you notice that this one, it has type object, but not all of them are. So in OpenAPI, you can have a one of, which is like a list of possible values. It sounds like a Rust enum, and it looks like a Rust enum, and we just map them to Rust enums, obviously. So we also, we insert the documentation. You can see the description becomes a doc string here. In Rust, your little // doc string is actually a syntactic sugar for writing an attribute with a little hash, square brackets, doc equals blah, blah, blah. So you can construct them just like you would construct any other kind of Rust source code. Generated code is very convenient for the person generating it. It isn't always pleasant to use. We really want to have a really high-quality Rust crate that feels familiar and pleasant to use. And this means your types should implement traits. We can automatically derive traits when they should be there. We automatically derive clone and debug and serialize, but we can't automatically figure out if an OpenAPI type looks like a number. And if it looks like a number and it smells like a number, you should be able to use it like a number. So for example, that angle type, we'd really like to be able to implement add on it. And there's no real way to look at an OpenAPI schema and know that this should work with add. So instead, we also support handwritten code. I'd say 95% of the crate is generated, but we basically have a little file called methods.rs. And you can write whatever handwritten code you want there. So we use that to implement a bunch of useful traits. We implement add for angles. We implement some useful constants like the 0-degree angle. Constructors, you can have one that takes in a number, and it knows its degrees or knows its radians, whatever you want. These little bit of handwritten methods go a long way towards making the crate more usable. I actually do have to use this crate day in, day out. So whenever I find a method that I wish I had there, I can just go back to the OpenAPI tour, and I can add these handwritten methods. And then when OpenAPI tour generates a new crate, it knows to look for this handwritten methods.rs file and leave it there. Don't overwrite it. We do the same thing for tests. We aren't going to automatically generate tests because we only know the rough kind of shape of the inputs and outputs. We don't know what processing happens in the server. So we handwrite a few tests as well. Basically, OpenAPI tour works by going through every schema, and it generates a Rust type for it. The schemas can be stored in a couple of different places. Like I said before, you can have a schema defined right there along the operation, or I can reference somewhere else in the OpenAPI spec. So we look for every place you could find a schema, and for each of them, we generate a type. Then for each operation, we generate an async function that sends the right kind of request and gets the right kind of response out. There's a couple of other little wrinkles. For example, pagination. It's really common to have a paginated API. If your database has 1 billion customers in it, firstly, congratulations. I'm very proud of you and your success. But secondly, you don't want to return all billion users if someone asks for them, because that'll probably DOS your server as it tries to buffer these all into memory. You really want to enforce the maximum amount of data you're willing to accept or return. So pagination is key. There's no real convention, or there's no definition of a paginated API, but there are conventions. There's a whole bunch of ways people do, in practice, tend to paginate their APIs. So we try to identify these when we're going through the schema, and if we identify them, then we generate two endpoints, two Rust functions to this endpoint. We generate a normal one, like you saw before, and we also generate an async stream. We generate a function that returns an async stream, and it'll manage getting the pages for you. So every time you pull data from that stream, it'll go back and send another request to get the next page from the API. Again, this goes a long way to making these common API tasks really good and easier to use than if you had a kind of naive, straightforward OpenAPI generator. A couple of shortcomings. This certainly is not perfect. Firstly, WebSockets. WebSockets are really important to what we do at zoo.dev. If you remember that demo from before, or the screenshot before, with that model, we're using a WebSocket to accept commands to update your model. We don't want to have to make people send a new HTTP request every time. That would be a bit unnecessary. So there's no standard for WebSockets in OpenAPI. They made the reasonable choice to just not care about WebSockets. That's fine. No one can care about everything. A lot of people do actually want to use WebSockets, though. They're pretty useful. So there's no real standard for how to declare them in OpenAPI. But there is, again, there are ad hoc conventions out there. We use Dropshot, which uses WebSockets. And so they've got their own convention for how to identify a WebSocket endpoint. And we try to, we basically return a request WebSocket, the request, REQ, crate. And there's no real way to say what that WebSocket should request. It's a fully bidirectional connection. It can take an arbitrary binary. So there's no real way to give a schema for WebSocket on top of that. There are other competing technologies. You can use gRPC or Captain Proto if you mostly care about these long-lived WebSocket bidirectional standards. I'm kind of thinking maybe at some point we should also support gRPC and Captain Proto, but we're a startup. We've got a whole list of things we'd like to support eventually someday. The other thing is that when you're doing all this code generation, it can add up to a lot of code, and you can have quite a lot of compile time to do that. Right now, if I go through our cargo crate and I look through all the deps that take the longest to compile, most of them are auto-generated crates, whether from us or from other APIs out there like Stripe. So these APIs can be really big. They just offer a lot of functionality, and they can be take quite a long time to compile, especially in release mode. Yeah, I don't know what to say. There's a lot of problems out there with just really big Rust crates take forever to compile. Everyone runs into it eventually. There's a lot of great blog posts out there about how to shrink them down. But eventually, I kind of just decided I'd rather eat the long compile time and be able to give a really high-quality API to my users. So we also offer things like a CLI and an Electron app. Boo, Electron, yeah. But it's, if you want to serve video across every single platform, it's really nice to have one consistent target for that. So if you don't want to use our API directly, you can use our CLI or our GUI apps for it, and that way you don't have to worry about compile times. Thank you so much. I really hope that this talk can help share. It's definitely a bit of group therapy for me because I spent so long worrying about getting PRs merged into keeping my API clients and servers and schemas in sync. And I really hope that you, if you're going through this experience as well, can now think about a better way. There's a whole heap of open standards out there. There's a whole heap of tooling in the OpenAPI ecosystem that can help you generate these tools yourself. And if there's nothing out there that's quite right for you, then go and make your own. It's just code. It can be a little intimidating at first, like a lot of things you don't know, but it's just code ultimately. And if you read the specs and you spend a bit of time learning it, it's totally achievable. Thank you very much.